Alright guys, in this video I'd like to talk about the relationship between combinations and Pascal's triangle. Let's first start by remembering the definition of combination. So combinations can be written as, so first of all let's write down what the letters mean. So let's let n and r be integers such that 0 is less than or equal to r is less than or equal to n. Okay, so n is at least as n is at least as big as r, probably, hopefully bigger, probably depends on what we're doing here. But the formula then for the combination of n choose r, we read this as n choose r. This is given by the symbol sometimes just c of n comma r, combinations of r objects out of a group of n. On your calculator, if you have a calculator still, you might see a button that looks like this, NCR, where the N and the R are subscripts on either side of the C. And the traditional way to write this is NR in parentheses. Almost looks like a fraction, but there's no fraction bar. This is not a fraction. And in parentheses here, you read this as N choose R. All right, now, how do we compute this? Well, we saw a formula in our notes that the formula for computing this is you first count the number of permutations, so that's n factorial, over n minus r quantity factorial, and then you divide through again by r factorial. So this right here, this formula is the formula for computing the number of combinations. R combinations are r choices out of n possibilities, right? So n choose r. This is the formula. Now, some conventions here, so this is kind of an introductory video, some conventions here, really one main convention is that 0 factorial has to equal 1. If any of you guys have heard of or studied the gamma function, you'll know why this is mathematically legitimate. The gamma function is an extension or a continuation of the factorial function. But for us, we're just going to take this as a definition. So 0 factorial has to be 1, and that just makes all of this work properly. And then from there, 1 factorial is obviously 1, and 2 factorial is 2 times 1, and then so on. So n factorial is n times all of the previous integers that come before it, all the way down to 1. And so that's what the factorial means. I think we probably remember that, but just in case, there's a quick review, and in particular, we do care a lot about this one, that 0 factorial is 1. Okay, so that's combinations. Now, what does this have to do with Pascal's triangle? Well, let's remember what Pascal's triangle is. Pascal's triangle, we will see this again in future sections because Pascal's triangle plays a role in what we call the binomial theorem, and that's going to be coming up soon in our study. So here's how we build Pascal's triangle. We start with we're going to build the triangle from the upper vertex down. We start with a 1 on top, and then we're going to work our way down row by row, and at every row we're going to kind of add a little more room, and we're going to spread out our 1s here. So row 2 is just 1, 1. And row 3, we're going to go down to 1, 1. But then in between, so in this third spot here, this middle spot, we're going to add the 2 previous that sit above it. So we have a 2 here. And then you continue on with this. So the 1s spread out. In this spot, we have a 2 plus 1 is 3. 2 plus 1 is 3. You're going to see a lot of symmetry. All right, I'll do one more row just so we can see how it goes, and then you'll see, I think you can see the pattern, right? But now the next row is going to be 1, 4, and then the next term is 6. 3 plus 3 is 6, and then 3 plus 1 is 4 again. So again, a lot of symmetry, and this pattern can be continued on, and if infinitely much, right? It fills out an infinite triangle here. But what's the significance of it? Well, notice we can look at these diagonals. These diagonals right here are all 1s. This diagonal, I should say, is all 1s. Up here we can put, say, a 0 if we want, and then this diagonal counts from 0 up, right? And so this is going to be our n. We're going to call this our n. So this is the n of the row that we live in. So that's the number of the row, essentially, right? And that's going to be the n in our combinations. Now, as we move our way from left to right, if n is 0, there's nowhere we can go, right? We just have 0 for r, in other words. So the r is going to be the row identifier, so the position in the row. So the one that's the row that has been kind of outlined on this diagonal, that's row 1. this is row 0, right? And then as you work your way down, you can get more and more rows. So row 2, row 3, row 4, etc. Okay? When I say row 2, row 3, or 4, I'm not counting the rows downward. I'm saying that that's the entry in the row. So let me be more clear. For example, let's look at this one. This entry is in row number 4, so that's what comes from this box, right? So here n is equal to 4, and the entry position from left to right goes from this is not the next row, but this goes from 0 to 1 to 2, and this is the number 3 entry from left to right, so that's r equals 3. And of course this would be r equals 4. These are the r values, so that's what I mean when I say the row. I mean the entry in the position in the row. So as you go down the diagonal, these position numbers count up as well, because the further down you go with the n, the larger n gets, the more possibilities you have for moving across the row, right? So the positions in the row. And so what it turns out that this number right here, this number 4, is exactly n choose r. So this is the n and the r. And you get the n choose r. So in other words, in this case, 4 choose 3 is equal to 4. And we can check this, right? Because remember how this is computed. So 4 choose 3 is going to be equal to 4 factorial divided by 4 minus 3 factorial, which is 1 factorial, times 3 factorial. And if you just write out what all these terms mean, this is 4 times 3 times 2 times 1. This is 3 times 2 times 1, and then just 1. And at this point, a whole bunch of stuff cancels, right? So 3, 3, 2, 2, 1, 1. This whole thing is just 4 over 1. And so this is indeed 4. And that is the entry in Pascal's triangle. It turns out that the entries at every stage in Pascal's triangle, if you follow this convention, then let me write it out here. So the entry in the rth position of the nth row of Pascal's triangle is always n choose r. Okay, and so this is a major factor. This is another way. The formula is better, obviously, because you can just compute as you go, but the pattern is nice, right? And for smaller, combinations, drawing the triangle is not really that much work. So if you have very large numbers, you don't want to draw the whole triangle. But this relationship, though, is important, and we will see this again moving forward, that the Pascal's triangle is closely related, if not, we could say, built out of combinations here. So the one last thing I will say is, just by observation of this triangle, if we believe this, by the way, there's been no proof here, this is just observations, but if we believe this, then just by observing the triangle, we can see that n choose r is equal to n choose n minus r. These are the same. There's symmetry here, whether we count from right to left or left to right. So I'm going to put a question mark here and leave this as a thought exercise for you guys. If you can prove it, then we believe it, then we can use it.